Hello, everyone, and welcome to today's webinar, Applications of EBSD for Analysis of Deformed High-Temperature Materials. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. I will attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we will follow it up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Dr. Ashton Egan is an Alexander von Humboldt Research Fellow conducting postdoctoral work in the Department of Materials Science and Engineering at the Friedrich Alexander Universität Erlangen-Nuremberg, as well as the Center for Nanoanalysis and Electron Microscopy. He earned his PhD in Materials Science and Engineering at The Ohio State University in May 2023 under the direction of Michael Mills and continued there as a postdoc. Ashton's research involves the design and mechanical behavior of high-temperature materials with emphasis on deformation characterization using electron microscopy techniques. He was the first to characterize local phase transformation at deformation-induced microtwins and show its strengthening effect, as well as perform atomic resolution energy dispersive X-ray spectroscopy on LPTs at superlattice intrinsic stacking faults and microtwins in superalloys. The bulk of his PhD and postdoctoral research has been completed at the Center for Electron Microscopy and Analysis, also known as CEMAS, at The Ohio State University, where he also served as an SEM manager. Now over to Ashton.
Hi, everybody. Thanks for coming to my talk, and thank you very much for the nice introduction. So today I'll be talking about some applications of EBSD for analysis of the alloys I work on, which are deformed high-temperature superalloys mainly, but I also talk about titanium in the back end of this. So today is really meant to be sort of a I guess quick, not quick, it's quite long actually, but it's going to be a basically just showing some ways I use EBSD in my day-to-day research, and not so much a deep dive into niche EBSD techniques. So what I'll do here is give a quick EBSD refresher, just so we're all on the same page. Give a motivation, just why we study aerospace alloys and specifically nickel-based alloys, what nickel-based superalloys look like in terms of the microstructure and deformation characteristics that are relevant for this talk, and the alloys that I'll be talking about. And then we'll dive into our 3 case studies. And these are basically, the first 2 are parallel cases, where I'll talk about using EBSD for electron channeling contrast imaging of the alloys that I've deformed in creep. In a parallel study that's basically EBSD for taking atomic resolution stem fib lamella, which I use for further analysis of said CECCI. And then a third case, which is analysis of an additively manufactured Ti-64 alloy and showing the texture evolution via direct recrystallization and grain boundary sliding. And then we'll take your questions at the end. So without further ado, I'll dive into it here. So what is EBSD in a nutshell, right? So essentially here, what we're doing is shooting an electron beam down at our sample, our specimen, and these electrons are inelastically scattered throughout the specimen. And basically, these electrons will hit atomic planes in the Bragg condition, and you'll get this cone that comes off, which we call Kossel cones. And these are basically just inelastically scattered electrons from planes of interest that satisfy the Bragg condition, right? And at intersection of the screen, the EBSD screen, the phosphor screen of the detector, basically you'll get lines from these edges of these planes, right? So where you see a line is actually where the plane is basically in real space. And the bandwidth corresponds to their d-spacing, and where they intersect, like here, is the zone axis. So basically what we can do is use these to figure out where we are in the crystal, and where we're looking at basically the orientation of grains. And this is very analogous to what we see in TEM Kikuchi patterns, which I have another picture of here. So this is basically the setup practically in an SEM where we are shooting an electron beam down the column at our sample, which is tilted to 70 degrees. And basically, the Kikuchi pattern comes off onto the detector, and this is what we see on our screen. And these patterns, once they're here, go through a series of different steps to index them. First being the Huff transform, and then actually IDing these, which goes through sort of a voting of what the computer thinks this is. And then we can define some orientation of these, and which common is Euler angles. But there's a lot to get into there, and let's just not get into the weeds of all the specifics of voting and Huff transform and the different ways we can define, the crystal, right? If you want details about this, Steve Niezgoda gave a really nice talk in CEMAS's Beyond the Scope discussion series. So I'll leave that to Steve to get into the nitty-gritty of what EBSD actually entails. What's important for us here is what we need practically to look at some metals and actually characterize the deformation characteristics, right? And so what we really practically need here for the sake of this talk are basically three things. One is an IPF map of the material. This is an inverse pull figure. And so each of these colors is representing a different crystal structure or crystal orientation in my samples. And this is a nice large IPF map that I took using CEMAS's velocity EBSD detector. So I think this is about 2 by 2 millimeters maybe in size. And I think this took maybe like 20 minutes to collect or something like that with the velocity camera. So very powerful. And this is taken at, I think, 0.5 micron step size. And we can see, lots of fun colored grains. Okay, so what do these colored grains actually mean? We can look at our IPF legend to figure that out. And so basically I've drawn a cube here for the main three corners of the stereographic triangle. There's the cube face, right, 001. There's sort of a down the corner view, which is 111, and then along the edge of a cube, which is 101 type. And so these are basically the three different main colors you'll see and the gradients between them to determine how this crystal is oriented. And so another salient thing is the Euler angles, right? And so this is a kind of complicated picture off to the right here. But basically, this is how we're determining what the crystal is relative to some reference frame, right? And I like this little image from Wikipedia. I'm more of a visual guy, so I think this is very easy to understand. Basically, you would have some reference, which is your XYZ plane shown in blue. And then our crystal orientation is given by rotation from that original. So basically, there's three angles that describe it. The first is a rotation about the z-axis. The second, a rotation about the new x axis after that z rotation. And then the third angle describes rotation about the second axes that we do right there. And so you can kind of see how these three rotations are used practically on the sphere. And that's all we really need here to talk about what we're going to see in the rest of the talk here. So back to superalloys. Why do we study aerospace alloys at all? And so the reason basically is performance, right? Nickel-based alloys specifically are used in the hottest section of jet turbine engines. So therefore, they have a very strong dependence on the thrust and fuel economy of these engines, right? So what I always like to tell people, and I think this is a fun fact, is that a 25 degrees C increase in the operating temperature of the engine will improve overall efficiency by 1%. And that might not sound like a ton, but actually this can be like billions of dollars in overhead fuel costs over the lifetime of a fleet. And so when we're talking about high temperature, we're thinking about creep, or at least I think about creep as the limiting factor at super high temperatures. And so far what we've done over the last, and not we, I guess I wasn't alive during this time, but over the years, scientists and engineers have slowly pushed the temperature capabilities up for these nickel-based discs and blades as well. And now what we're looking at is this very sort of high temperature operating regime up here in the 750 to 800 degrees Celsius range. And so these are the materials I work on. And we're doing this basically to improve efficiency, reduce carbon emissions, and save money. And so what these alloys actually look like in terms of the microstructure, well, they're polycrystalline. So we have a range of different orientations of different grains. And inside of one of these grains, we have a two-phase gamma prime microstructure. So what you're seeing here, the gray phase is gamma phase, which is just FCC. And then we have a coherent gamma prime phase, which is ordered L12. This is just the ordered version of FCC, where there's a different atom that sits on the cube faces and the cube corners, right? So this is pretty simple. And basically, the way that these deform can vary based on the grain orientation. So for the purposes of this talk, I'll just talk about microtwinning mainly. And so we're going to talk about these 001 type grains. So if I were to take a single crystal and compress it along the 001 axis, basically I would get superlattice intrinsic faults shearing the precipitates. And these are little pictures basically showing what's happening here. And because we're at creep, diffusion is at play. So basically what we'll have is Cottrell atmospheres of cobalt and chromium, which are gamma formers, and they stick near the leading partial dislocations as they shear through these gamma prime precipitates, right? And so once this original shearing happens, a fault called a superlattice extrinsic fault is left in the wake. And then this can, upon further elemental segregation, form a local eta phase. Okay, and so why would we want this local eta phase? Well, there's a route that this can take that's not so good for performance. The local eta phase is one of the preferred ways that we would like this to deform. But, oh, don't want to let it happen there. Kind of skipped ahead. But basically, the quote unquote bad way that this could deform or go is more gamma stabilizing elements segregating to these defects. And this is what we call a gamma like local phase transformation. And so my research is basically trying to prevent this thickening from happening and thickening into these deleterious microtwin boundaries because microtwins rapidly accumulate strain, and rapidly is not something you want to hear if you're talking about failure of a disk in an airplane, right? So what we can do is then prevent this by a local high phase transformation, which is what basically I did my PhD studies on. And this is stabilizing the microtwin boundaries via a local phase transformation to chi phase. And that's all good. And this is basically what I'm going to talk about, is how we determined this local chi phase and the microtwin boundaries using EBSD along the way. And so this is kind of what a creep test looks like in terms of creep strain versus time. And these are two alloys that I'll be talking about comparing with ECCI. And these are a low niobium and a high niobium sample for the purpose of this talk. And let's just simplify it, the only difference between these two alloys in terms of microstructure and composition is a 1% niobium increase in the high niobium alloy. So otherwise, the grain size is the same, precipitate size is the same. For all intents and purposes, they're the same, except the high niobium alloy has 1 atomic percent niobium addition. And as you can see, it performs a lot better in creep, and by better, I mean a lower minimum creep rate. And so that's good. That's what we want to see. And our alloy design did well. We made a better alloy. But why, right? And so this brings us to our first case, which is using EBSD for ECCI analysis of these crept superalloys, right? So I crept these both to the same percent strain, and then in another test, took them to rupture and found that one was better and one wasn't so good, okay? And so I want to look at the deformation structure of both. And so how do I do that, right? How do I go from EBSD maps that I can take telling me something about the orientation of each of these grains in this alloy and go to something like this on the right where I can see defects shearing through precipitates. And recall that I mentioned about microtwins. Basically what we want to look at and focus on are these sort of red grains, which are 001 type grains, and we'll just limit our discussion to that because this was the critical thing for the study. So to back up just a little bit, what is this ECCI thing that I'm talking about, right? Like what is electron channeling contrast imaging? Basically, oops, sorry, I think I clicked a button here and made it go out of presenter mode. Okay, so what is electron channeling contrast imaging, right? So basically, if I just put a sample into the SEM and insert my backscatter detector, I'll get backscattered signal from the sample, as you can see in the far right here, or far left, I'm sorry. Let's see, laser pointer. Right here. And right now, this is just at some arbitrary condition in terms of diffraction, right? If we were to think of this in a TEM and diffraction contrast imaging, I'm kind of just in between bands, not in a two-beam condition, and I'm not really seeing any defects. And this is what the grain of interest looks like on the far right. You can see it just looks like a grain using a backscatter detector. You get some contrast based on its orientation, but nothing special jumps up at us. And what I can do instead is tilt and rotate the sample using the Euler angles such that I get into a channeling condition, which is similar to a two-beam condition in TEM. In fact, I can choose which G vector I excite and basically get a channeling contrast image on the far right that shows defects. And what's going on here basically is in this condition, we're channeling electrons through the sample. Imagine you're shooting the electron and it's going just between some planes and just down into the sample. It's being absorbed and not coming back to the detector. And that's where the dark nature comes from in this grain. But when we have a defect, basically because this disturbs the crystal lattice, we'll emit a lot of backscattered electrons, and we can start to see white traces. And these are defects. And in my case, they're superlattice stacking faults and or microtwins. At the ECCI scale, it can be kind of hard to distinguish between the two unless you do, very careful kind of G.B sort of experiments. But from what we know of these alloys, basically, if you see straight lines that are going through both gamma and gamma prime, as many of these do, those are microtwins. And typically, we don't want to see these microtwins, or so we thought. And then maybe you can pick out certain features like this one where it's isolated to a precipitate, and that's an SCSF generally. Okay, so I explained, okay, we tilt and rotate this thing, but how are we doing that? And how do we use EBSD to actually practically do this, right? So here's a case of our grain that I showed earlier, and it's an 001 type grain, which we're interested in because of microtwinning. And so great, I took an EBSD map and I have this of my sample. Now what do I do with that? Well, first I use the OIM software that EDEX has to record information about the crystal. And then I choose this highlight grain function, basically. And then I've highlighted it, and I chose highlight color black, so it's obvious. And then what the software will spit out to me basically is these Euler angles I was talking about, right? And so now I have the average orientation of this grain. And what I can then do with that is use this as an input to drive to some condition of interest. Let's just say the G vector is O2O type. And I have this input now. I know what the orientation of the crystal is. I know where I want to drive it to, but how do I actually do that, right? Well, you have a really smart guy named Greg Sparks, and he works at AFRL and was also in my group at Ohio State. And basically, he made this code called cECCI Wizard. And for Aprio-based systems, this will take a basically input for an Euler angle, convert it to basically a vector, and then you can choose another vector that you're interested in, and it will match them up. It will tell you, okay, what minimum tilt and rotation combination do I need to actually drive to that vector, right? And then I type those in, basically tilt and rotate my stage, and then all of a sudden I can see defects. And so the key here basically is in the code and Greg. So basically there are, I think, several folks out there that have codes that are similar to this. Greg is one of them. And I think he'd be happy to share and discuss if you would actually like that. But that's sort of not my deal. I don't code. So he's like the master wizard that makes this all happen. Okay, so this is actually how we do this, right? We take Euler angles from OIM, plug them into Greg's code, and then like magic, we get cECCI images. And so what we can do with these then is first some just qualitative analysis, right? Looking back at our two tests, and these ones are taken to rupture. So you can see that there's one, the red one, that performs significantly better. And if we look at the deformation structure and cECCI for both of these, we can tell several things. One of it, which is the density of the defects. The not so good alloy had a lower line density, and the other one had a much higher line density. And also note the scale bar, right? So if you look at the scale bar, it also appears that the good alloy had smaller features, whatever these superlattice stacking faults character are, or microtwins, they're smaller of some sort and less dense. So those are just sort of qualitative things. And in addition, there's multiple slip systems in this alloy and the bad alloy and single slip happening in the good one. So that's all great. So we can just survey on large scale many grains of the 001 type and compare all of these. And then we can move sort of into a quantitative route and start using the Euler angles for other things. So basically what we could also do is take our Euler angles from EBSD, and we don't necessarily have to even go to a specific diffraction condition. We could even just look for grains that are dark and then go to them, look at the defects, and then use the Euler angles from those, sort of random cECCI conditions to figure out things like the slip system that's might be active and what Schmidt factors are going on. So this is just a picture of the EBSD geometry and how we define our three axes. And so using rotation matrices, we can take the Euler angles, convert those into a specimen sort of reference, and then do some vector math, or not vector math, I'm sorry, matrices math to basically determine plane traces and trace angles of those traces. So, and then with the Schmidt factor, basically, we can tell for basically a given slip system, and if we know the crystal structure, so FCC alloys, it's a 111 type plane and a 110 type Burgers vector, or if they're partial dislocations, 112 type Burgers vectors, and we can calculate the Schmidt factors for the various slip systems using the orientation of the crystal as well. And so doing something like that looks like this. So for the grain on my left, basically we can type in the Euler angles into a code, and this is one that one of my former colleagues, Connor, developed. We can determine things like, okay, for a trace that is at 108 degrees relative to our viewing screen, what is likely the slip system or the slip systems that are operative, right? And so there's three. And then we can ask, okay, so what is the Schmidt factor for the possibilities here? And then also, what are the intensities of the diffraction criteria we're under? And typically, the highest Schmidt factor is the one that will be operative. And also, this has quite a high intensity. So it's likely to be, or at least these traces, the bar 1, bar 1, bar 112 direction type slip system. Or it could be this one below it, but we're not going to get into that. So basically, okay, this makes sense. All of these defects are likely to be on the highest Schmidt factor slip system, and we kind of have an idea of what's happening here. But we need to go further. And what if we actually want to look at these defects and determine their character, their segregation tendencies, all of this sort of thing? Well, what do we do with that? And so that moves me on to the second case, which is once we have all this great ECCI data, and we found some defects that we like, or don't like, I guess, but we want to study, how do we actually then do that from a specific grain and looking at specific traces that we see in ECCI, right? So going from now EBSD and ECCI to the generation of STEM fib lamella for atomic resolution analysis. And just to give a quick preface here, if you don't know much about TEM and atomic resolution analysis, you basically want very, very thin foils, something along the lines of maybe 50 nanometers, if not thinner, if possible. And we want these basically to be, for the purposes of doing EDS, which is chemical analysis, basically untilted once we load them into the TEM. And this has to do with shadowing of the EDS detectors if we tilt, but also when you tilt a foil, you effectively make it thicker to the beam direction. So basically, we want to just load this TEM foil and be bang on its own axis and just start doing analysis. And so how do we do that, and how do we leverage EBSD to let us do that, right? Because we could just put a fib lamella down on any of these given grains and some random orientation, pluck it, and then we could drive to a zone, and do some atomic res, but it's not going to be meaningful if that's not good data and if it's not the zone we were interested in, and not ensuring that it's the defects we see in ECCI, right? So, okay, how do I now take this foil for atomic res STEM? So the first thing to do is you find a grain you're interested in, or the region of interest that you looked at in ECCI. And in this case, it's a near 001 oriented grain relative to the compression axis. So these red ones, basically. And specifically, we want to look at this grain that we had in an ECCI condition. Okay, and so this is the part that can take some time, is going between SEM and the grain map. And if you've spent a lot of time staring at these, you end up becoming good at, figuring out, okay, this is what this grain looks like, and now I need to move like maybe 50 microns here, but I'll save you the hassle of doing that, and here's the grain that I was studying, right? And so, okay, great, we found the grain. Now what? So now what we want to do is figure out where the plane trace is of the possible 011 type fib foils. And so the reason I'm taking the plane trace of 001 or 011 is that these traces that we see here, these lines, I want to look basically edge onto them. So I want to look edge on to the faults that, or microtwins, that have sheared, basically to see if there's segregation along them, and do EDS, and also determine whether they're intrinsic, extrinsic, or microtwins. And the easiest way to do this is basically to look down a 011 zone axis and see them directly, and by doing atomic res. Okay, so basically what I do is I go to the interactive highlighting settings, type in, show me the plane trace of 011 type planes in this grain, and then great. Then I use these two other tools that are basically an overlay of the crystal and also the planes, and I plop those on top of my grain of interest. And you could just use basically the plane traces, but for my own sanity, I also like to see the crystal on there, just to make sure, okay, I chose the right plane and this makes sense to me. And so what we're seeing now here is the cube face, basically, of the unit cell looking at us, and that's what we want to see in 001 type grain. And then what these lines tell us are basically the traces of the 011 planes in that crystal. And so the length of these lines tells us how close they are to intersecting the surface. And so there's two that are equivalently long, and this might make sense because it's the two diagonals of the cube. And so by taking either diagonal, you could look down an 011 type zone axis. And so which one do we actually take? Because there's two, right? And now we kind of have to think about, our ECCI orientation, and how these are like laid in real space. And so basically, if we look at the traces of these deformed traces, or these stacking faults microtwins, they're diagonal. And so to look down the edge of them, we would have to lay the platinum along this 011 type plane trace. And so what I've done here is just throw in a vertical rectangle into PowerPoint along with the grain map, and then I just rotate it so that it matches the trace. And then I ask PowerPoint, okay, tell me exactly what rotation I just used to do that from vertical, and it's 60 degrees. So what we can then do is go to an Aprio SEM or a fib, put platinum down in the same way. In other words, what I mean is draw a rectangle in our platinum deposition pattern, exactly like this. And then in the advanced settings, we can tell it, okay, now rotate that pattern by 60 degrees. And so it will. And then basically we've perfectly aligned the platinum cap to the trace of the interesting plane. And so you can just take directly bang on foils that need very little, maybe like maximum 3 degrees tilt if you do this very, very carefully. I've even seen some cases where like you put the foil in and it's bang on zone axis and you don't have to tilt at all. And that's a really happy day. It's a good work day when you do that. And so you're probably asking now, okay, well, that's great for 001, that seems like an easy case. How about other grain orientations like 101, 111, and even goofy orientations like a 123? And so I've also done this because we check the other grain orientations to see what type of basically deformation modes we have active there. That's a little beyond the scope of the talk. But in terms of physically how we're doing this, it's the same, right? We can draw a cube and the traces of in this case, 011 type planes, and then do this for, say, the 01 or the 101 type or 111 grains. And that might seem intuitive. And you might ask, well, why don't you just use a pole figure to do this? And the reason is accuracy. I like to just be very accurate because of doing atomic resolution and have to tilt less. And also for a case like the 123 grain normal, which is basically right here, you get a pole figure that looks like this. And then, okay, well, I can't lay a platinum cap horizontal or vertical because we're a little off from both cases for where our 011 plane trace would be. So I like to know exactly what that angle is. And basically, there's no guesswork. You can just lay platinum right on here. And so this works out really, really well, basically. And you can do this with basically any zone axis you want to and any sort of crystal system you want to. You can just ask OIM software to do it for you. Instead of staring at pool figures for a long time and trying to guess, okay, well, this is the way I need to draw this, or trying to find a magic grain that lines up either horizontally or vertically based on the other two orthogonal directions from the beam direction. Okay, so now he basically had done this. You know, we found our 011 type cap or 011 type trace, put the platinum cap on it, as you see in the right, and then we thin this foil. It's nice and straight and also atomically thin. So this case on the right, you can see all these little defects that I had showed in ECCI in this foil, which I really like. I think this is a cool picture. And basically, we're completely straight in our fib foil. So, okay, we can just load it in the TEM and go. And so then what are we actually doing in the TEM? So this is CEMAS's DNST. This is a pretty cool picture of the room. Basically, the TEM sits in one side, we sit in the other. And this has a very small or a very high resolution. It's a 0.63 angstrom resolvable distance. And I operate this at 200 kV. And so then once we have one of these foils, we can do several things. We can use bright field and annular dark field, basically detectors to take diffraction contrast images and correlate this with the ECCI images that we saw and go, okay, we see the same distribution of defects, these same traces, and for instance, these inclined things are stacking faults. And then we can do what I was talking about earlier, which is looking directly down the 110 type zone axis. We can see basically all of the atomic columns, and this is a microtwin from the sample that we just took. And then what I can do once I have the atomic res or at the high magnification is do EDS at atomic resolution and figure out where these species are segregating to in the defects. Okay, so back to these microtwins that we had looked at earlier. So here they are. And this is what basically these look like in the wild. So here's a microtwin on the left and then an SESF on the right. So basically the thing you see on the right evolves into the thing you see on the left. And you can see there's some bright trace along the interface of the microtwin, and the SESF is also kind of bright. And the reason being is the segregation characteristics. So for these local phase transformations, we get basically a denuded area of aluminum and nickel and some enrichment of what we call LPT formers. In this case, cobalt, tantalum, tungsten, and then niobium is also there. And so we can overlay these on top, and basically you can see where all the atoms are and where the atomic species are as well. So that's really useful. Okay, so how do we combine all this, right? So we have some creep tests with two alloys that vary only by 1 atomic percent, but somehow one is better. And we've done EBSD on the sample, which has given us ECCI images of the deformation. And then we've used EBSD again to pull thin foils and look at these in atomic resolution. so we can measure the size of them. And then we've done this for the other alloy as well, right? And so how do we combine all this together to tell us, well, why are these two different? And something I'll point out is the thickness of both of these defects. You can see the twins are basically different sized. And we know all of these traces are twins because I spent a lot of time going around randomly to these traces and looking at them, and they're basically all microtwins. And how do we get quantitative about this and tell us something, kind of important? And like I said before, there's some qualitative things like, okay, low niobium has thick twins and multiple subsystems active, high niobium, thin twins, one slip system. And then we can look at each of the actual twin thicknesses and quantify these. So low niobium was average 31,111 planes thick. High niobium was an average of 8. And it's a little out of the scope of the discussion, but the high niobium alloys were also enriched heavily in niobium at the microtwin interface, which is actually what restricted the thickness of them, right? So it's, local phase forms. You can't shear that phase. So other thickening dislocations don't want to cut through that bright area and thicken it. And so we can make sure that all the strain that we've accumulated in this test comes just from these microtwins, or how much, I mean, we don't know in the beginning, right? And we can use this equation here, which is basically the strain due to twinning is related to, which this is basically the line density of the twins times the displacement of each of these. And so we know this displacement of these is from partial dislocations that are 1/6, 1/12 type. And so what you do painstakingly is draw lines across these images, count the number density of defects hitting the line in ECCI, and then use the atomic resolution images to figure out what the thickness of each of these microtwins are. And because they deform by a certain number of Shockley partials, we can then figure out, okay, well, for this thickness of twin, this average thickness, this is the strain due to twinning. And we can generate some sort of combined ECCI and STEM twinning strain determination, right? So what we found basically was that all of the strain comes from twinning, and that's great. That's what we expected, right? Based on just qualitative kind of arguments. And that one of these has a bit more happening on the secondary slip system. And the reason here is that this high niobium alloy has, with its high density and thin twins, basically restricts partial dislocation movement either through them, so they prevent the secondary slip system, or alongside them, which is basically what makes it stronger in creep, is you have to make many of them in order to get to the same amount of strain as you would this sort of thicker twin, and it takes a long time to do that because of segregation related effects, right? Diffusion. And so in a nutshell, we've just used all of this EBSD kind of characterization to solve a metallurgical problem, right? Without it, we wouldn't have been able to do ECCI in a controlled fashion. So, this data was all collected from me driving around to various 001 grains, using Euler angles as an input to drive them to a diffraction condition, taking a bunch of images, sitting down for hours and measuring line densities, and then, on those same grains, using the Euler angles to determine, okay, this is how I have to lay the platinum to take fib foils to look at these, essentially without tilting and at atomic resolution. So, it's a very simple, relatively straightforward technique in terms of getting the data that I acquired, right? I just take basically a quick EBSD scan and have Euler angles, but this can be very powerful information if you use this correctly. And that's sort of the takeaway from these first two cases, right? It's not anything too fancy, but it's very practical, and this is how we can use EBSD sort of in our everyday research lives to make things easier and solve problems. Great. So now I'll pivot a little bit after I drink coffee. Okay, so now I'll pivot a little bit and talk about a third case, and this is less TEM and ECCI, and more just looking at EBSD and what this can tell us for analysis of additively manufactured alloys, like what the texture evolution is basically from, okay, this is the as printed and heat treated material, now we deform it, and then how that evolves with deformation. And so basically this was a project by Dr. Calvin Stewart and his student Jacob, and they work in the materials at Extremes research group, which Dr. Stewart heads. And they came to me with this interesting problem. They said, hey, we did all this mechanical testing of these alloys. Can you do some EBSD or microscopy analysis and let us know, what you see and how this might help explain the phenomena of our tests? And so I said, yeah, let's do it. And so that's what I'm going to show now. So just to give a quick background on, what exactly the problem is that we're trying to solve. They have some Ti-64 electron beam melted builds. So basically you raster an electron beam to build up layers of material by introducing powder, melting them, more powder, and then you just do this for many layers and make a thick sheet of metal, basically, or a block of metal. And so additively manufacturing like this is gaining popularity. I mean, has gained popularity. And there's a couple of reasons, and some of them are like rapid prototyping, right? You can build these very quickly and do studies on them fairly quickly using complex geometry. So you can 3D print basically any part geometry you want, things that you couldn't do with conventional machining even. And as a sidebar, I believe GE right now is now using additively manufactured fuel nozzles in their engines. So this is actually practical and being used, out in planes. And then reduction of costs and reduction of waste material, right? So if you can build your part to near net shape, you don't have to worry about all of this machining loss and basically the value added problem where you're paying a guy to sit there and machine this for an hour or something, right? So it can be a lot more cost effective as well. But because this is such a new thing basically, and these alloys have not traditionally been additively manufactured, you basically have to qualify these materials. So I know that even when you just make a new alloy, it can take like 10 years for the conception of the alloy being designed and to the point where it's actually used in an engine. And so basically we want to do rapid qualification, right? And the way we do this is via accelerated testing. So this is much faster than conventional testing is. And one of the ways, and the way I'll talk about in this talk that this is being done is with dynamic negative stress testing. And basically on the right, you can see what this is. So basically we could do 2 creep tests at 2 different stresses. And that's these little dotted lines, these conventional creep tests. So we could do this first one and then do another one, and then basically repeat this for many stresses at the same temperature or different temperatures and get a lot of data. But this takes a really long time because creep is a kind of something you want to happen slow. So this can take hundreds of thousands of hours over many parts. So we desire a way to do this faster, right? And maybe in one go if that's possible. And so this stepping test method basically is one in which, and this is shown in red, as you creep at one stress, once it reaches the minimum creep rate, you basically drop the load or the stress, and then you transition to a different minimum creep rate that would be basically similar to the other stress, right? So you can kind of see the slopes of these are very similar to the conventional tests. And so this lets us test a lot of different stresses rapidly for whatever given part we're trying to look at. And this is sort of what this would look like for a complete test, where creep strain is on the Y and time is on the X. And we'll get for each one of these different stresses that we use, and we're decreasing basically, you get to a steady state. You kind of reach instability where you might start to ramp up into the tertiary regime, which you can kind of see at the end of the test here, this accelerating tertiary regime. And you basically keep lowering the stress right before you start to tail upwards. So you get a bunch of minimum creep rates from the given stress that's used for them. Okay, and this is great. Okay, we designed a test that take less time. Now what? So now we can test all of these different build directions, and I might have not mentioned this before, so let me quickly go over that. So many of these additively manufactured parts have some sort of anisotropy in the way the grains are oriented. And so what was done here basically is several orientations of bars were taken relative to the build direction. And you can see all these different angles, 0 to 90 degrees, and then a vertical sample along the basically build direction, right? And we wanted to see, okay, how do each of these basically variations affect the creep properties, or do they even? And the answer is yes. There is some clear anisotropy related to the build direction. And to sum it up here, these top two graphs, basically at 0 degrees, this has a highest minimum creep rate, which read bad, and the lowest time to rupture. So it breaks quickly, right? The vertical sample had the lowest minimum creep rate, which sounds good, and the longest time to rupture. And then so the other directions sort of fill in with 60 splitting sort of the maximum and minimum, or the highest and lowest creep rates. And so then what these folks have done in Dr. Stewart's lab is use a strain energy density method for evaluation. And basically what they're doing here is taking the area sort of under the curve here, and you can see this in both sort of things, and to get strain energy to failure, which it's called WF, right? And then average strain energy density rate, which is this other WF little dot on top, which is just basically the area under the curve, which if you know material science, that's the energy input, right? So what we desire in the end basically is a large energy dissipation capacity of the material. In other words, you can put a lot into it, but we want a low dissipation rate. So you want to dissipate this energy quickly instead of very rapidly. And so a perfect alloy would have a high a high strain energy to failure and a low average strain density rate. So that's basically what we're after. And you can see here that, where is it? The vertical sample should be here. Yes, so the vertical sample indeed does sort of have this, but this graph is kind of hard for me to read. So we can do, oh no, there's something there. Well, ignore this nice EBSD map in the upper left-hand corner. And basically what we can do is normalize this, or normalize both of these functions based on the total amount of material and the time. And so we basically get this graph of acceptable and non-acceptable regimes. And the vertical line, or the normal from this sort of slope of 1, the magnitude of this will tell us how good or bad basically an alloy is. And so from this graph, we can read, okay, the vertical is quite nice, 0 is quite bad, and 60 is in the middle. And now this brings us to EBSD. Why is it like this, right? So what we did is take these bars, section them, look at the grips, which would give us an idea of what the original and therefore strain-free microstructure is like, and then look at the sort of gauge and look into the fracture area and then kind of towards the grip. And this gives us high and intermediate strain regimes, respectively. And so then back to EBSD, we generate a ton of EBSD data. And these are all EBSD maps that are taken from these various places. So at the top, there's labels showing you grips, which are sort of where I'm indicating now, mid-gauge and near fracture for each of these orientations. So 0 is this first row, 60 is the middle row, and vertical is the last row. Okay, and so what happens, what's happening here, right? So this sample is being deformed via some sort of dynamic recrystallization mechanism that's coupled with grain boundary sliding. And I've put a couple references up here if you're interested. There's other folks who've studied this in detail. And we basically just use their theory to sort of explain what's happening here. And so some main takeaways here are, main components that go into this are, and importantly, the equilibrium subgrain size, i.e. the size of the grains, Berger's vector, shear modulus, and applied stress. But the latter three should remain the same, right? So what's changing likely is the subgrain size. So we've also looked at the grain size for each case and how it evolves with time. And you can kind of, really need the graph to see this. You can see it in the EBSD maps. Basically, our best sample, it seems, maintained almost, so also to note that these are tested in the X direction, right? So stresses in the X direction of these. So for the vertical, we have these very long grains along the axis of stress, which will evolve sort of over time. And you can tell there's some sort of a substructure forming by, might be hard to tell, but the gradient in color in some of these grains, and also basically the separation of similarly oriented regions, right? So like in this blue area, you can tell it looks like there's a bunch of subgrains of 10 bar 10 type orientations. And then finally, near the fracture, where the strain's the highest, you have all these tiny little grains. And so basically what you're seeing here is dynamic recrystallization, where a dislocation substructure is setting up during, with accumulating strain. And then once this happens, these grains slide relative to each other, which leads to superplasticity. And so after staring at these for a long time, basically what we determined was that the orientation of the long axis of these grains are different, right? And you can kind of tell that in the grip section where vertical, like I said, is elongated along the stress direction, and 60 and 0 degrees are not, right? So these are oriented in slightly other kind of directions. And so what this effectively changes is the effective size that the dislocations, in other words, see as they travel through the grain. So if the dislocation is traveling left to right in any of these images, it can travel a lot further in the vertical sample than it could in the 60 or 0. So basically what you're doing is getting rapid pile up in the 0 and 60 degree samples. And basically the substructure develops very quickly. And you transition to grain boundary sliding relatively quickly in both these samples. And then even in some, you get creep voiding, which in the 0, which is the worst, you can tell regions that are circled in black, where basically creep voids had formed. And then the vertical sample, this is delayed a bit, where the substructure develops for a longer time, which you can tell between the grip and mid gauge. They're not exactly the same, but you can tell definitely the mid gauge has quite a bit less dynamic recrystallization than the other two. And then this delays grain boundary sliding. which eventually does happen if you look at the really high strain input near fracture region. So that's basically what we determine just by looking at the EBSD maps, is that, the orientation of the long axis of these grains and the way that affects the effective equilibrium subgrain size is kind of the root cause for why the vertical sample is able to basically absorb more energy, take in more, deformation and delay sort of the rupture and leading to like a lower minimum creep rate than the other two samples. And that's why it's acceptable, but 0 and 60 are not really acceptable, right? So with that, I think I've reached my time. And so just to recap, I've talked about EBSD for 3 different cases for ECCI analysis, and then parallelly taking using Euler angles to, once we have this ECCI analysis, extract fib lamellae, which we can basically not tilt very much and we're good for atomic resolution. And then a third case where we used EBSD to analyze the texture of these Ti-64 bars that underwent direct recrystallization, dynamic recrystallization and grain boundary sliding. Yeah, and so with that, I'll turn it over to the other folks. Yeah.
Hey, thanks, Ashton, for the talk. It's really enjoyable always seeing some of the work that we're doing here at CEMAS in more detail. Or everyone out there, go ahead and I think you can go ahead and type in some questions now. But in the meantime, I'm Daniel Vecti. I'm a research associate and SEM manager here at CEMAS. And a quick plug for our masterclass in scanning electron microscopy. The goal of this course is kind of to have nice practical hands-on experience on the microscope for different users. So we kind of have 2 different ways of running the course this year. So either there's kind of a manager track where you'll be able to watch all of the lectures and then have time to work with the instrument managers on the microscopes themselves, either on your samples, or the more classic way that we've run this in the past is time for all the lectures and then a 2-day hands-on in-person training workshop where if you're a researcher on the microscope quite a bit, it's helpful to come in, see a microscope. You'll work with instrument managers here at CEMAS on the microscope. If you're interested in this, there's a registration link down at the bottom, and we're just opening up registration this week for it. So hope to see a few people from the class on that.
Thanks, Dan. We've had a few questions come in. How did you prepare the nickel superalloy sample in the ECCI analysis?
Yeah, so this is actually non-trivial. So basically, you want to be very careful as you polish. I usually start on like 600 grit from a deformed sample, and then carefully removing the deformation layer from each previous grit. So I go 600 grit, 800 grit, 1200 grit, and then use a diamond paste of 6 micron, 3 micron, 1 micron, and then colloidal silica for roughly 2 hours. And this is 0.05 micron colloidal silica. And so basically care must be taken to remove, the prior deformation, and a good general rule of thumb is like 3 times the grit size, roughly. And in my alloys, like that's kind of overkill, but it works really well. And then what you're seeing is only the deformation that you've imparted with testing and not grinding and polishing. So, yeah.
Okay. When you do the ECCI with the SEM, do you physically tilt the sample against the E-beam in order to get 2 beam conditions?
Yeah, so actually physically what you do is go to the stage controls and type in the rotation and tilt required to get onto a two beam condition. Yeah. In fact, you can actually do this even if you don't have a code. You can still tilt and rotate and kind of look at how the grain changes and kind of do this in a uncontrolled way just by looking when the grain turns dark.
What working distance is used for ECCI analysis?
Yeah, so I use basically I darn near touch the insertable backscattered electron detector to maximize both the signal and resolution that I'm getting. And I think this is something like maybe 4.5 millimeter working distance. 5 at, the furthest.
Okay. How do you identify different phases in single crystal grains?
Yeah, so in a single crystal, I think you're talking about gamma and gamma prime, maybe, which are indistinguishable if you're looking at, just an EBSD map. But in TEM, you could tell the difference between gamma and gamma prime. If you're talking about ECCI, basically, I think maybe I did show this in one of my ECCI images. Let me quickly go back here. You can actually see the gamma and gamma prime. So this is one example. So sometimes also the gamma prime will lightly etch. So you can see kind of like these little circles that are surrounded by a bright fringe. Those are gamma prime precipitates. And then sometimes you can also see them right. Yeah. So you can also maybe see you can kind of see the gamma prime precipitates relative to the matrix. The gamma prime precipitates are these kind of like squiggly blobs.
Okay. Can you talk more about how to determine the active slip system using the computed Schmidt factor?
Yeah, so I think basically what you're asking, I can answer with this slide that I was just on. Basically, what you do is figure out, there's only 12 slip systems in FCC crystals. So basically what you do is you just, your beam direction, right? And your axis of the stress. And so I think what I do is actually, okay, whoops, wrong slide. So what I do basically is orient my samples such that the beam direction and the axis of stress are the same. So basically my beam direction is along this third axis and right here when I'm untilted. And so by using that, the angle between the force you apply and then what would be the projection of the plane and given Berger's vector that could exist. There's a couple that could exist or a few that could exist. And so basically what you do is you just use all the permutations that are possible, calculate what the Schmidt factor would be, assuming that the axis of stress is the beam direction. And of course, you could basically put the axis of stress somewhere else, but you need to know where it is. And then you can use the Euler angles to determine where the planes and directions are of the crystal, permutate them all, and then you just assume that it is the highest Schmidt factor, that is active. And in ECCI, we can also figure out the traces of all these planes. And obviously the traces will all be different. So you draw a line, for instance, 108 degrees. And there's only a couple possibilities for a trace angle of 108 degrees and only a few Schmidt factors, right? And you would just assume that it's the highest one. It could also be the second highest, right, in theory, but you would have to go to TEM to actually figure out for sure what the character of the dislocations are that are propagating the stacking faults or your slip. Yeah.
All right, thank you. If we analyze the microstructure using the HCP phase in EBSD, can we observe SISF and SESF directly?
That's probably unlikely given the size of them, right? So even the twins, right, are pretty thin in these materials. And SESF is only a few. I think I have a picture of an SESF just for reference here. Here we go. Yeah, so if you look at an SESF, the short answer is no. The short answer is no, but the long answer is no, because the interaction of the beam is much larger than the actual local phase. So it's only localized stacking that is HCP or FCC. But you might be able to do something like a image quality map and see where bundles of these are. But no, you can't tell where SCSFs are. Microtwins, maybe if they're big enough. I've seen that done because if the microtwin becomes large enough that you can reasonably detect a pattern from within it, you could see that. But SCSFs and SISFs, no, because they're too small, basically, and not real crystals.
Okay. Which SEM model did you apply the ECCI analysis with?
Yeah, so this is the Aprio-based system. Dan Vecti probably knows all of the more niche details about what is actually, the specific setup of these. But essentially, it's just the Aprio-based system with the Trinity column, and I use an electrostatic lens basically to improve my resolution for this. Dan, any other? I don't know if you want to chime in on that.
No, that's, yeah, most of the work's done here on our Aprio, our Thermo Fisher Aprio SEM. So either thin column detectors, or like Ashton was saying earlier, for ECCI stuff, he's using quite a bit of the insertable backscatter detector, which is great with that really large angle for collection.
Yep.
Okay. Can you see the defect structure in the superalloy with the FSD or Prius detector?
In the FFT, you can. So if you do like an FFT of the image I have up here right now, you would get reflections that are associated with the twin, say. So you will get reflections that are based on, a defect in the image. And what was the latter thing you said? The FFT or the what? You said Prius detector?
Prius. Yep.
I don't think so, but I actually have never tried. I don't often use the Prius detector, but maybe microtwins I could see it being possible. With SCSFs and SISFs, I really don't know, but I don't think so because of the size.
Okay. What was the accelerating voltage used for ECCI analysis, and how does it relate with tilt angle and rotation?
Yeah, so there's a couple different, and you can use a couple different settings. I've done ECCI both at 5 and 20 kV. I think on one of these slides, it actually specifies what my settings were for that image. Maybe not. But in reference to the angle, I'm assuming you're talking about the angle of the beam or the convergence angle, which is honestly unknown. I don't actually know what the convergence angle of the beam is. But these, for instance, were taken at 5 kV with a current of 0.8 nanoamps. So obviously, the smaller the current, the smaller the probe size, but also less signal, right? And I think what they quote for the Aprios is something like 1 nanometer resolution, kind of guaranteed. But I think in practice, Dan and I have seen a bit better than that. But because it's such a refraction technique, you can see these in both, like 5 kV and 20 kV, perfectly fine.
Okay.
And that doesn't affect the tilt and rotation of like the actual the software that we're using, right?
Okay. Why don't we observe the beta phase in titanium EBSD?
So in this one, it was a low beta kind of heat treatment. So there wasn't much to observe. And also, as such, I didn't index it. So I only chose alpha as the one that I was indexing, knowing that there wasn't beta there. That's basically the short answer.
Okay. Is it possible to quantify the dislocation density from ECCI analysis?
The dislocation density, I'm sure, yeah, I'm sure it is, especially if you can see, you know, the density, but you also kind of know, at least for these defects, you can kind of get an idea probably of, right, I guess how many dislocations have passed to give you this many traces, but you would have to make some assumptions there. I do know that they do sort of like geometrically necessary dislocation content analysis just from EBSD. Oops. Yeah, but I would imagine there's ways in which to do this if you can see single dislocations, but I'm not an expert in that sort of thing. So.
Okay, just a few more questions. How important is it to have the accurate lift-out foil orientation for the atomic resolution TEM EDS analysis? And is it practically feasible during TEM observation?
Yeah, so here, this is a good slide to show, I guess, why it's important. So there's a couple of factors that are at play here. So you can see just in this little schematic, there's a sample, right? And then it's surrounded by 4 EDS detectors. Or in this case, there's a variety of different architectures for doing EDS and TEM. And in this case, if the sample is not exactly flat, so let's say I tilt it towards one detector, in my detector, I'm talking about the Super X detectors, you would then shadow the detector from the opposite side. So to maximize counts in EDS, you'd basically want there to be no tilt at all so that you can get the most counts. And so, you want a high amount of counts, a good signal to noise ratio for doing such a thing, because it takes a decent amount of time, the sample drifts a little bit, and so you want this to happen in some reasonable, feasible time. So that's one of the reasons. The second reason is, like, physically, if you tilt something with some given thickness, like you could even take your phone and kind of do this, kind of look at it. If you were to put an electron beam through a zero tilt sample of thickness 50 nanometers, it will effectively increase the thickness if you were to alpha tilt to, say, 20 degrees, because the path that the electron beam is taking is now longer through the sample. So you could have increased your sample thickness by a decent amount. And so to get really nice atomic resolution images using the Hanoff detector, you want a really thin foil. But practically, you can do atomic res analysis with thicker foils and with higher tilts. It's just you don't get the data quality that you get with thinner samples. So practically, yes, this is very feasible. This is how I do most of my sample prep, and I don't have to tilt very much to get to sort of the zone axis. Sometimes, and most times, I'd say it's easily less than 5 degrees, but it can be much, much less than that.
Okay. How is the EBSD plane related to the fib lamella normal?
I'm sorry, how's the EBSD what?
The EBSD plane related to the fib lamella normal.
Yeah. So I actually have I think, pretty decent picture here showing this. So basically, the trace of the plane here is where I've drawn the fib platinum. And so I can do this. So basically if you look at a cube, along one of the diagonal lines, you can draw corner to corner. The FOIL normal of that would be 011 type. So the trace of a 110 type is basically the normal of a 110 trace is a 110 type. So that's the relationship. So I drew this along the trace of the plane. In other words, like basically the edge of the plane that I've drawn with the arrow is the platinum, if you want to think about it that way.
Okay, one final question. How do you determine the rotation, tilt, and angle for ECCI analysis?
Yeah, so as I described earlier, that is where Greg Sparks' magic comes in. So basically, you take an EBSD map, get the Euler angles of the grain you're interested in, and basically that gives you a vector, right, that you could describe the average orientation of, well, you can convert this into, I guess, a vector in, you know, sample orientation space, right, an XYZ vector, which would be the grain's normal. And then you can, you know, figure out how much tilt and rotation it would take to put that vector along another vector, make it parallel to some given, maybe, for instance, 020 type net vector. So basically, it's just driving the sample with tilt and rotation using basically matrix operations, or what is the word I'm thinking? Sort of coordinate transformations, basically, in MATLAB. But Greg is the wizard that does all this actually encoding. I just use it. So he would be the person to, if you want to figure out like how you would practically implement this in a code, Greg is the guy to talk to do that, because that's way above my pay grade.
Cool. That's all the questions we have, Ashton.
Oh, great. Thank you.
So thank you very much for taking the time to present today. Thank you everyone who attended, and we'll see you next time.
Yep, thank you.